Welcome to solverfy.
Okay, we have a series of pairs of molecules, and we need to determine if they are constitutional isomers or not. What I would remind you is that the double bond equivalencies formula, right, is essentially a count of the number of double bonds or ring structures in a molecule, right? And the rule basically says that if you introduce a double bond or some sort of cyclic structure in a molecule, then you are reducing the number of hydrogens that a straight chain, as compared to a straight chain molecule, would have. What I mean by that is, let's say we have a 4-carbon chain, and the formula for carbons and hydrogen that relates number of hydrogens to carbons for a straight chain alkane is that we do C4, and then the number of hydrogens is going to be the number of carbons times 2, and then we add 2 to that number. So for a 4-carbon chain, we would get C4H8 plus 2 is 10. Every time we introduce a double bond or a ring structure, the number of hydrogens decreases by 2. So this structure, in which we take the same thing but add a double bond, has the formula C4H8, right? That's number of carbons times 2 plus 2 minus 2. If we add 2 double bonds, all of a sudden we have C4H6. If we add a cyclic structure, all of a sudden we have C4H4, decreases by 2. And so that's the tool we will use to answer this question. Consider question 1. We have a 4-carbon ring, and then a 3-carbon ring with an additional carbon. Both of these have 4 carbons, and both of them have exactly 1 cyclic portion to them. So we can predict that the formula will be C4H, and then it's going to be number of carbons times 2 is 8 plus 2, and then minus 2. So C4H8. Same thing here, C4H8. So these are constitutional isomers. Let's look at number 2. We have a 5-carbon chain, a methyl on carbon 2, methyl on carbon 3, and a methyl on carbon 4. And for the other molecule, we have, again, a 5-carbon chain, but now we only have a methyl on carbon 2 and a methyl on carbon 3. So we can pretty much right away tell that we have 1 less carbon altogether, right? So there's no way that these could be constitutional isomers. So I forgot to say 1, the answer is yes. 2, the answer is no, right? Because we don't have even the same number of carbons. There's no way that could be constitutional isomers. Let's look at number 3. Here we have a 4-membered ring, and coming off of that is a 1, 2, 3 carbon chain. And in our other molecule, we have a 1, 2, 3, 4, 5 carbon chain with 2 methyl groups on carbon 2. Again, via our formula, we know that whether or not the number of carbons is the same, the number of hydrogens definitely isn't, right? Because we have 1 cyclic structure here and none here. Nevertheless, let's say 1, 2, 3, 4, 5, 6, 7. There's 7 carbons, 1 ring, so that's going to be C7H14. Whereas this, we have 1, 2, 3, 4, 5, 6, 7 carbons. But because there are no rings, it will be, for the number of hydrogens, it'll be 7 times 2 plus 2, or 16. So no, these are not constitutional isomers. One last pair. Molecules. 6-membered ring with a double bond and a methyl group sticking off. And again, 6-membered ring with a double bond and a methyl sticking off. All we've done really is move this double bond. But if we wanted to check via formula, we know there are 7 carbons, so it's C7, right? And we know that there's a double bond and a cyclic structure, so it'll be 7 times 2 plus 2 minus 2 minus 2, right? Or C7H12. And likewise, C7, 1 double bond, 1 ring, 7 times 2 plus 2 minus 2 minus 2, right? That's 16 minus 4, that's 12, H12. And yes, these are constitutional isomers.